Okay. Okay, good afternoon, everyone. So welcome to the colloquium today. It's my great pleasure to introduce our speaker today, Professor Gunther Roland from MIT, who is also my former mentor. So Gunther, he got his PhD at the University of Frankfurt, working on the experiment at SPS at CERN. After that, he spent a few years at MIT and Frankfurt and CERN before joining the MIT faculty in year 2000. So that was a year when the relativistic high-volume collider at Brookhaven has started. And at the time, there were 4 experiments at RHIC. So right now, there's only one. The STAR experiment is only one. Currently, is running at RHIC. So RHIC is also a member of the STAR collaboration. So back then, Gunther was the physics coordinator and the deputy spokesperson of the Phobos experiment. Phobos is one of the 4 experiments. It's a smaller one, but very dedicated. About 50 people working very closely with each other, and I have the pleasure to be on that team and got my PhD from Phobos. So after Phobos is completed, Professor Roland moved on to the CMS experiment at CERN, which started in year 2009, and he became the convener of the heavy-ion physics group in CMS, played instrumental role in the early stage of the program and set up a very productive group at CMS. And let me mention that during that time, he made a number of achievements, and there are a number of achievements under his leadership. To mention a couple, the development of the idea of triangular flow, that's a seminal contribution to the field, and the discovery of the quark-gluon plasma-like signature in the proton-proton collisions that was completely unexpected, and also he pioneered some of the early measurement using the jets, particle jets, to study the property of the quark-gluon plasma. A few years later, he decided to kind of shift his focus back to Brookhaven. He became the spokesperson of a new experiment called sPHENIX. So that is a new experiment that's being constructed and almost finished construction, which will take full advantage of the upgraded RHIC accelerator to have high luminosity collisions to perform precision studies. And this is so we're going to hear. So Gunther has been the spokesperson since 2016 on sPHENIX. So we're going to hear first-hand information about this exciting new experiment from Gunther today. So welcome.
Okay. So thanks, Wei, for the very nice introduction. The invitation, and arranging for very nice weather. I'm impressed. I assume it's like this year-round. So I'm going to talk about Hot Qcd, studies of the strong interaction under extreme conditions, and what we plan to do to extend these studies with a new experiment at the Relativistic Heavy Ion Collider called sPHENIX. And what you see on the right here are some pieces of sPHENIX that have been recently installed, and I'll, of course, talk more about what the status of that experiment is. But before that, I, of course, want to start with an introduction to Hot Qcd and try to explain why Wei and Frank and myself think that's an extremely interesting field of physics to study. Okay, so let's start with the big picture, universe, and a quick reminder of one of the most fascinating things in physics, and I'm sure one aspect of physics that has motivated some of you to take on this field of study, namely the fact that you can understand most of the totality of everything that goes on around us in terms of just a very small set of underlying interactions. Of course, one can quibble about the exact number here, but so for starters, we can think about 4. Gravity, which you all know, keeps you sitting in your seat. The electromagnetic force, which well, allows us to use, for example, all the electronic equipment here. The weak force, which I think to a good approximation is the source of all our power. And then the strong force, which I find to be the most interesting of the 4. And should we take a short break and figure out why our colleague cannot hear anything? Test, 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 check, check, check. Can you hear anything? Question mark? Anybody out there? I don't know, no sign of life. Okay, I guess we have no choice but to continue. Sorry about that. So my favorite, the strong interaction. So why do I think that the strong interaction is the most beautiful interactions of all of them? And for that, we can do sort of compare and contrast of the simplest systems that you can think of, let's say on the electromagnetic side and on the strong side. Okay, one thing that I'm sure you've all seen and learned to love in your introductory quantum mechanics lectures is the hydrogen atom. And when you think about hydrogen, what you find is that many of the properties of the assembled hydrogen atom can really be understood as the sum of its parts plus some small perturbations. And they can, these properties can be calculated and measured with fantastic precision, some of the most precise measurements that are done anywhere in physics. Okay. If you contrast that with the simplest, or one of the simplest QCD system that you can think about, the lightest stable QCD system, proton, which like the hydrogen atom is a bound state of some smaller constituents, what you find is that unlike for hydrogen, the properties of the proton, like for example its mass or its spin, are not simple sums of its constituents, but are really emergent properties that are dominated by effects related to the dynamics of the interaction between the constituents rather than the simple properties like mass or individual spin. So QCD is and the strong interaction is all about emergent properties that cannot be readily calculated from just two-body interactions. And that makes it, well, sometimes frustrating to study, but also fascinating. Now, why is that so? Where's the fundamental difference between QED and QCD that leads to that? And since the last 50 years, we know what the building blocks of QCD are: the quantum chromodynamics, the theory of the strong interaction. It's a quantum field theory, like QED, the theory of electromagnetism. The basic building blocks are similar. In QED, we have electrons, which are point-like fermions, and photons, massless bosons. In QCD, we have, again, point-like fermions, the quarks. And we have massless bosons, the gluons, that provide the force, that are the force carriers, mediating the interaction between the quarks. And so far, these two different interactions of nature look in their fundamental structure quite similar. Now, one thing that is different is that in QCD, unlike in QED, both the fermions, the quarks, and the bosons, the gluons, carry charge. Of course, not electric charge. The quarks also carry electric charge, but the charge of QCD, the charge of the strong interaction, which we call color charge. Don't worry about the word color here, just accept it's a charge carried by the fundamental constituents. Okay. So what we, however, see is that although the basic elements are somewhat similar, there are fundamental differences in the observations we can make. In QED, it's no problem to observe individual photons or individual electrons. In QCD, however, the smallest system that we can observe directly in our experiment are composite particles called hadrons. Classic examples of hadrons are protons and neutrons, or things like pi mesons, but there are many, many others, hundreds of other hadrons that you can assemble out of quarks and gluons. And so fundamentally what we can see in QCD, in the experiment, are not the fundamental pieces of the theory itself, quarks and gluons, but we always see these composite objects in which the quarks and gluons are stuck. That property is called confinement, and this is really one of the fundamental differences between QCD and any of the other interactions. Now, where does that difference come from? And here what we have to think about is really the role that the vacuum plays in understanding the interactions between and the properties of the particles that we see. Of course, vacuum here does not just mean empty space. It means empty space that is at any time filled with quantum fluctuations where, for example, electron-positron pairs or quark-antiquark pairs or gluons or photons appear out of the vacuum, do something for a short amount of time, and then get returned into the vacuum. And I mean, as you know from studies of QED, the effects of these quantum fluctuations are, at least in QED, subtle, but calculable and measurable with fantastic precision. For example, one of the effects is that the QED coupling constant, alpha, Sommerfeld's fine structure constant, is not just a number of 1 over 137, invariant under all conditions, but if you probe at smaller scales, length scales, or higher momenta, the coupling constant actually changes, and in QED it grows because of the screening of the color charge at large distances due to vacuum fluctuations, which becomes smaller as you get closer to the color charge. So the polarization of the vacuum is directly visible in QED. And the same effect also exists in QCD, except that in this case, as I mentioned, the gluons also provide a contribution. The photons don't carry electric charge, so they then don't play a role on the QED side. The gluons, however, carry the charge of the strong interaction, the color charge, and therefore also contribute to this polarization effect. And in fact, they reverse the sign of the polarization effect such that the QCD coupling constant becomes smaller as you go to smaller distances or higher momentum transfers. So the gluon contribution leads to anti-screening and therefore a running coupling constant that decreases as you go to larger distances, larger momentum transfers, or inversely increases to the point that it becomes impractical to actually talk about the coupling constant as you go to very small momentum transfers or large distances. Now, I would like to explain exactly how the gluons do that, but when I asked Frank Wilczek about that, he told me that, well, you have to do the calculation, and apparently that's what you have to do, not just to understand it, but also to get the Nobel Prize for it. So I guess we have to take, well, we don't have to take Frank's word for it. We have also seen this effect directly in measurement, looking at alpha s as a function of distance. So the fact that our coupling constant varies very strongly is called in the high momentum transfer limit asymptotic freedom. Even inside hadrons, the quarks, if you hit them very hard, behave like quasi-free particles. Inversely, as you go towards large distances, small momentum transfers, you get the property of confinement, although that, to the best of my knowledge, has not been shown analytically, but you can do it, see that in numerical solutions of QCD using so-called lattice QCD. Okay, so the vacuum really plays an essential role in our understanding of QCD, leading to the question, how can we understand this better? And one very naive or very sophisticated proposal is what happens if we change the properties of the vacuum? For example, if we take a region of space that has the quantum numbers of the vacuum and put a lot of energy in there, heating it up to a very high temperature, how does that change the interactions between the strongly interacting particles? That's a proposal that is almost 50 years old, and that over the last decades we have been pursuing experimentally. So what is the expectation if I take my composite QCD particles, like a proton, and I put it into a region of space at extremely high temperature? Well, if you ask a smart person like David Gross, he will tell you that if you heat the world to a temperature of a few hundred MeV, corresponding to a few trillion Kelvin, 100,000 times, maybe 10,000 times hotter than the interior of the sun, 100,000 times hotter than the interior of the sun where fusion happens. If you go to temperatures of a few trillion Kelvin, what will happen is that your composite particles, the hadrons, will melt into a plasma of liberated quarks and gluons. I mean, this is, of course, then in a regime where we're talking about a relativistic system, meaning that the particle number density is no longer a constant, but density and temperature are closely related. And in particular, this corresponds to well, a few trillion Kelvin and mass densities of 10 to the 15 kilograms per cubic meter. And then, as David Gross suggests, if you take the world, or at least some small region of space, and you heat it up to these extremely high temperatures, or you compress such a system, what you will get is a transition from a world of hadrons, like protons and neutrons, etc., or mostly pions, to a world in which quarks and gluons can move over larger distances, are no longer confined, just because at these extremely high densities, related to the high temperatures, the notion of a particle stops making sense once many of them occupy the same volume element. So the idea is take the vacuum, take a region of space, heat it up to extremely high temperature, and see what are the properties of this extremely high density and temperature state. How are the interactions of quarks and gluons with each other modified under these conditions? Now, when I started doing this many years ago, centuries ago it feels, the idea was that what you would get was essentially an ideal gas of quarks and gluons. And of course, now I'm really happy that that isn't what happened, because it's difficult to think of a more boring system than an ideal gas. And as I will try to show in the following slides, what we have observed is something that is much more interesting. So let's see, what does a QCD system look like once we go to these extremely high temperatures? Of course, first we have to think, how do you create a system that has a temperature of a few trillion Kelvin and a mass density of 10 to the 15 kilograms per cubic meter? Well, what you do is you go to particle accelerators. I've shown the two accelerators at which the experiments I'm going to talk about were performed. One is the Relativistic Heavy Ion Collider. You already heard about that. Brookhaven National Lab started operation in 2000. and accelerates atomic nuclei to energies of 200 GeV per proton or neutron. Now you remember the mass of a proton is about 1 GeV, so the kinetic energy of these nuclei after they've been accelerated is 200 times larger than their mass, so highly relativistic, hence relativistic heavy ion collider. 10 years after the heavy ion collider, we started to use another machine, the Large Hadron Collider, most of the time used for proton-proton discovery physics, but 1 month per year also used as a heavy ion machine, colliding lead beams at collision energies that are another factor 25 larger than at RHIC. So what happens at such a machine? Well, you start with 2 fully stripped heavy ions, gold at RHIC or lead at the LHC. You accelerate them to close to the speed of light. Of course, you accelerate them by sending them around the accelerator many, many times until they look like Lorentz contracted disks. Then they smash into each other and create this red matter. That's our quark-gluon plasma at extremely high densities and temperatures. But then, of course, the system doesn't just sit there, but it expands in all directions, cools down, and in the end, once the density is sufficiently low, it turns again into the hadrons that we know. So the whole, the time this process takes, well, it's all moving at close to the speed of light. So the time and length scales are just given by the size of the nuclei. You may know that a lead nucleus has a diameter of about 15 Fermi, 15 times 10 to the minus 15 meters. And therefore, the typical time scale at which things happen here is size divided by the speed of light, which is 10 to the minus 22 seconds or so. So this process it happens very quickly and in a very small volume, but that's the best we can do to generate temperatures that are as high as the ones that we need to create the quark-gluon plasma. So the whole process is over after about 100 Fermi over C, time scale 10 to the minus 21 seconds. And now we want to see what are the properties of that hot piece of matter that we have created here. What are the initial conditions? Which temperature and density do we actually achieve in a heavy ion collision? What are the best degrees of freedom to describe the system? Is it in terms of quarks and gluons? Is it in terms of other quasi-particles? And what are its properties, like hydrodynamic transport coefficients, viscosities, or other thermodynamical quantities? So that's what we want to know, but as you can guess for yourself, that's not so easy, because as I mentioned, the collision process is over after about a few times 10 to the minus 21 seconds. Okay. And then we observe these collisions, the final state of the collisions, in our detector. Our detectors are, let's call it 10 foot as a scale. Speed of light is a nanosecond per foot. So it takes 10 nanoseconds for the final particles to actually go through our detector, which is many times longer than the duration of the collision actually was. So what we see is just the debris of the quark-gluon plasma long after it is gone with our detectors. What you see here is actually an event display from the CMS detector that shows the signals in our detector from tens of thousands of particles that were produced in a single collision of 2 lead nuclei at the Large Hadron Collider. Okay. So how do you take this and learn something about the state of matter that is long gone by the time your detector sees it? Well, there are 2 fundamental approaches to that. One is you can use probes that don't actually interact with the quark-gluon plasma. They get created in the quark-gluon plasma, but then don't interact and just reach your detector without further modification. For example, photons, which do not interact strongly, and therefore can pass essentially unaffected through the quark-gluon plasma after they are produced. So you can use photons to measure the temperature of the quark-gluon plasma, like you would use photons to measure the surface temperature of the sun. What you find, a somewhat complicated analysis that I'm not going to describe in detail here, is if you focus on this low momentum part of the photon spectrum, which is related to the sort of black body radiation of the photons, of the quark-gluon plasma, this part, then the slope of that part is related to the temperature. As I said, there's quite a bit of analysis involved, but you can translate it into a temperature of about 3 trillion Kelvin, indicating that in these heavy ion collisions, we indeed make a state of matter that is as hot as is needed to transition from the world of hadrons into the world of the quark-gluon plasma. There's a little caveat, and this is of course an average temperature because photons from all stages of the extended collision process pass through the quark-gluon plasma, and therefore we integrate all of them, and the initial temperature that we reach should be even higher than that. Okay. So that's one way to learn about the quark-gluon plasma. Use probes that are not affected by the medium. Another way, which I will explain in a little bit more detail, is to use probes where information is preserved through momentum and energy conservation. So one thing that you might want to learn about the quark-gluon plasma, so of this form of matter that is sitting there, is what are its hydrodynamic properties? Is it more like a gas? Is it more like a liquid? One way to characterize that is through the viscosity, in particular the shear viscosity of the material. Here are two examples, and this is water, this is honey, examples of two liquids with very different shear viscosities. Shear viscosity, you should think about that as controlling momentum transport between layers of a moving liquid, in particular differentially moving layers of a liquid, where smaller viscosity means that the liquid flows more easily. It also means that momentum transport across layers is more difficult. Okay? So an ideal gas where stuff can just fly from one end to the other has a high shear viscosity relative to its density. So what about the quark-gluon plasma? How do we measure the shear viscosity of the quark-gluon plasma? Normally what you would do is you would, for example, put your liquid between two rotating disks and then see how is momentum transferred, or what is the torque between the two differentially rotating disks. Well, that's not what we can do. But what is possible is to start the quark-gluon plasma with a particular initial shape. Nature does that for us automatically, and then see how does it expand from there. And here is an example of what one could expect. You start with the state that is more highly compressed in one direction than in the other, just by virtue of its anisotropic shape. And then you let go, and because the pressure gradients are not isotropic, just from the shape, the acceleration in the hydrodynamic expansion will also not be isotropic, and you will get more acceleration of the matter in this direction than in this direction, leading to a transfer of information from coordinate space in the initial state to momentum space in the final state. And the lower the shear viscosity is, the less of the information will get lost in this process. And the whole process can be described by hydrodynamics with the shear viscosity or shear viscosity to density ratio as a transport coefficient. So this is ultra cold atoms. Let's see what happens in the quark-gluon plasma. This is an event display of the CMS experiment where the beam goes into the board or comes out of the board. So this is in the transverse direction in the plane perpendicular to the beam direction. And this plot shows how much of the energy of the produced particles is flowing in a particular direction. And what you see here is that this is not circular, but it's a little bit squeezed in this direction and a little bit elongated in this direction, meaning you have about plus minus 20% more energy going this way than this way, if you count the energy in small slices of angle, which is quite remarkable because this is the result of summing the energy of tens of thousands of particles. So this cannot be just a statistical fluctuation, but there must be some correlation between all these particles. So an emergent effect. And whoops, what we can do, if we move our slides in the right direction, is relate this effect to the initial shape of the quark-gluon plasma. Typically, if you collide these two nuclei, they will not hit right center on center, but with a certain impact parameter between these two centers. And therefore, the quark-gluon plasma will only be produced in the overlap region between them. And therefore, it will have a shape that is reminiscent to this shape of my ultra-cold atoms, with a short direction and a long direction. And the pressure in the center of the system, therefore, has gradients that are anisotropic. The pressure gradient is bigger in this direction than in that direction. And therefore, the matter in the course of its hydrodynamics expansion will be accelerated more strongly in this direction. So we start from here, we go through a hydrodynamic expansion, and that translates this initial configuration space anisotropy into a final state momentum anisotropy. And here, based on this event display, I can find this angle, and then I know that in coordinate space, the quark-gluon plasma that I produced was tilted in this particular way. These two angles, this I can see in experiment, this happened in 10 to the minus 21 seconds, are the same, within some fluctuations, of course. Okay, so I can do this squeeze and release experiment with my experiment on the quark-gluon plasma and can use that to determine its viscosity. And here's an example how viscosity plays a role here. This is ideal hydrodynamics with viscosity set to 0. And this is with a viscosity set to 1 over 4 pi. I will explain the particular meaning of 1 over 4 pi in a moment. And you see that what the viscosity controls is how well these sharp structures in the initial energy distribution, which are just random fluctuations in the initial state, how well do these sharp structures get preserved in the in the expansion process? And as I mentioned, the smaller the shear viscosity is, the more of this information contained in this initial fluctuations gets preserved. And if you increase the shear viscosity even a little bit, the initial fluctuations quickly get washed out in these calculations. So now what we can do is we can measure using billions of collisions components of the final state distribution of the particle that tell us about particular shapes into which you can decompose the final state distribution, the Fourier components of the final state distribution, which we can relate to fluctuations, the size of fluctuations, and distribution of fluctuations in the initial state. And what we see is that we can actually, with hydrodynamic calculations, depending on how you set the shear viscosity to entropy density ratio, describe the spectrum of these shape fluctuations that we see in the experiment between billions of collisions that we have taken. Conceptually, this is actually somewhat similar to using the final state cosmic microwave background angular structure to learn about the properties of the universe at an early stage, starting from the initial fluctuations reflected then in the final state distributions that we can measure today. And then, as you see here, again, if you vary the initial conditions and vary the shear viscosity, you get a varyingly good description of the observed final state correlations. Now, this is a program that has taken the field on the experimental and theoretical side the better part of 2 decades to finally arrive at both the hydrodynamic codes that can provide this description, understand the initial state fluctuations, and do the measurements. And today we can, for example, as a function of the momentum of the particles that we look at, or as a function of the overlap, the centrality, the overlap of the collisions that we look at, describe the observed anisotropy in the final state in various components with hydrodynamic calculations. And we can use the agreement of the calculations with the data to constrain the shear viscosity to entropy density ratio at the lower RHIC collisions, lower energy RHIC collisions, and the higher energy LHC collisions. And we find that based on our best efforts, this ratio is between 0.05 and 0.2. Okay, I can see that these numbers create enormous excitement here, or maybe not. So let me explain why you should be excited about that. What we can do now is we can compare what we have determined for the quark-gluon plasma in terms of its shear viscosity to all of the other known liquids in nature, like water, or helium, or ultra-cold Fermi gases, or even calculations trying to set a lower bound on how low the shear viscosity of a quantum system can actually be using sort of the toolkit from string theory. And what we find is that this value of 0.05 to 0.2 is not only lower than any of the other known liquids in nature, it is at the level of a lower limit that was determined for certain classes of conformal field theories, which are distant cousins of QCD, in a calculation that was done about 15 years ago, actually by now 18 years ago. And that puts the quark-gluon plasma in a quite unique position among all the forms of matter that are known, and it is related to the fact that it is that it needs to be understood as an essentially structureless, quasi-particle-less, zero mean free path, or close to zero mean free path liquid with strong correlations between its constituents in a similar class of materials as seen, for example, in this string theory calculations or in strongly coupled systems in other fields of physics. So that is well, one of the reasons why we keep going with this type of studies. It turns out that the quark-gluon plasma is far from an ideal gas. It's actually the polar opposite of an ideal gas. It's the most perfect liquid that we can create in nature. So let's look at some other properties of the quark-gluon plasma. Here, one QGP scattering experiments. What we can do is take a quark-gluon plasma and shoot something through it. That is how a lot of the most important things in nuclear and high energy physics were discovered in the last 120 years, from the atomic nuclei, protons and neutrons inside the nuclei, to quarks inside protons and neutrons. So you take a piece of matter and you shoot something through it. Of course, that's a little bit more difficult if your piece of matter is gone after 10 to the minus 21 seconds. So here the idea is to use quarks, send them through the quark-gluon plasma and see how they interact with the quark-gluon plasma. And what you have to do here is use probes that nature gives you, like jets. So what is a jet? Well, if you create a pair of quarks, quark and antiquark, for example, in the E plus E minus collision, at high momentum, high relative momentum between the two, they will fly away from each other at close to the speed of light. but of course, because of the property of confinement of QCD, they cannot fly away and show up in your detector. What happens is that they undergo a process we call fragmentation, where the quark and antiquark turn into hadrons, pions, kaons, protons, etc. And it is the spray of these hadrons that we see in the detector. But I think it's still fascinating to look at what is seen in the detector and understand that is directly related to the underlying diagram describing the interaction that produced a quark and an antiquark. You can even see in some events that one of the quarks radiated a gluon that shows up as a third spray of hadrons in your detector. Now what we can do is we can look at what happens if a jet or a pair of a jet in one direction and a jet in the other direction, because of momentum conservation, goes through the quark-gluon plasma. And this is an event display again from CMS that shows, well, here's one jet, there's another jet. This distance here is actually pi in angle, so they're back to back. But their momenta are far from equal. This is 200 GeV, this is 70 GeV. So the equivalent of the mass of 130 protons has gone missing somewhere. And it was well, radiated by this jet as it went through the quark-gluon plasma and has become part of this background. So this phenomenon is known as jet quenching, and it gives us another diagnostic to really understand the properties of the QGP. Most of the energy loss happens through induced gluon radiation as a quark or a gluon goes through the quark-gluon plasma and sees all the other color charges. And well, we can go one step further and take a process like this, where we have a quark scattering of a gluon emitting a photon. Remember, the photons just go through the quark-gluon plasma, and a quark on the other side. So this quark-gluon scattering, this is what it looks like as a sort of cartoon or diagram. This is what it looks like in the CMS detector, photon balancing the jet in a proton-proton collision. In a heavy ion collision, it can look like this: photon, 190 GeV, jet, 100 GeV, so 90 GeV of energy that this jet lost as it went through the quark-gluon plasma. And we can then relate this again to transport properties of the quark-gluon plasma. Let me skip this and just point out one more thing. I mean, this bullet going through an apple is actually more prophetic as a cartoon than one might think, because what you can see is how are particles in the quark-gluon plasma emitted relative to the jet that goes through it. And you see that here in the direction of the jet, you get quite a bit of emission, like here, in the direction of the bullet. But you also get some extra emission in the backwards hemisphere. This is the angle between the particle and well, the opposite of the bullet. You get also some emission here in the direction of that hole. So you can not just learn about the energy loss with jets, but also, again, about the liquid nature of the quark-gluon plasma. So now, where do we go next? And we have looked at various properties of the quark-gluon plasma, and I only gave a couple of examples of the measurements that we can do. But what I haven't explained yet is really, what is the structure of the quark-gluon plasma? What makes it different from an ideal gas of quarks and gluons? Or in other words, how does the QGP work? And this question, how does the QGP work? How do we go from the perfect liquid, the long wavelength behavior described by hydrodynamics, to free quarks and gluons, which we know from asymptotic freedom is sort of the high energy underlying interaction. How do we go from here to there? How does the long wavelength behavior emerge from the asymptotically free underlying interaction? And that's what sPHENIX is supposed to answer. This, again, is the sPHENIX experiment that you have seen before. For scale, this is the CMS experiment on which many of your colleagues here are working. You see, sPHENIX is about a factor of 3 or so smaller, meaning about a factor of 20 or so in volume, which actually translates approximately proportionally in the cost. So having a much smaller experiment is much more affordable than one of the big ones. The structure of sPHENIX is actually familiar to anybody who has seen a collider experiment before. So you have one beam coming from here, another coming from there. Collisions happen here in the center. And this is surrounded then by some onion, cylindrical onion of various detectors, starting from calorimeters that measure energy on the outside, then a magnet in between, and then tracking detectors that determine the trajectory of charged particles in the magnetic field on the inside, including a very high-resolution silicon-based detector that can look at particle decays that happen within a fraction of a millimeter away from the primary collision point. This detector is currently being built by the sPHENIX collaboration. It's about 400 people, have been working on this for the better part of the last decade, with construction actually starting shortly after 2016. As in always in these big collaborations, we have collaborators from all over the world. This is a small fraction of the collaboration at one of our meetings. This is the schedule that we are trying to follow. We are about here, moving the detector into the interaction region. We hope to reach this stage where everything is assembled and ready for beam in 5 months from now. Usually when we have an internal meeting, I have a counter with the exact number of days that are left, not many. Let me just prove that this is where we are, moving this device from the assembly or staging area into the area where the beam is later going to appear. This is shown here. So these are people working at close to the speed of light, getting this detector from the assembly area into the interaction region. This is, well, gives you a good idea of the size of the device. It's about 1,000 tons of equipment that we're moving here. Quite heavy, but factor 20 lighter than CMS. Not quite, I mean, this is about 800 tons. Okay, so that's where the detector sits right now. We actually moved it also a few feet in that direction. And this is where assembly continues. And as I said, we have about 5 months left. So this, I think, was a nice match to this part of the schedule. But not everything always goes according to schedule. This, for example, is a picture from April 11th of this year. This is a UPS warehouse somewhere in California. These are UPS trucks, as you can see, that burned down in a warehouse fire. I don't know which one, but one of these trucks was carrying our beryllium beam pipe, which is an extreme, I mean, it's a few centimeter diameter, very thin walled beryllium structure, a couple of meters long. If you could replace it, it would cost about $500,000. But there's nobody that could make it on the time scale, remake one on the time scale from this fire until our beam comes in April of March of 2023. Fortunately, our colleagues in STAR had a spare beryllium beam pipe that they were willing to lend us and gift us, and that we are now machining to match to the rest of the beam structure in our interaction region. Otherwise we would have been screwed. And we're not shipping this thing anywhere. We're doing all the machining at Brookhaven. This is not going anywhere. And well, there are other stories I could tell, but in the interest of time, let me just point out that sPHENIX will start running in early 23. We have an agreement to run for 3 years. 3 years may seem like a long time, but for a collider experiment, that's very short. We will see if there's any further running. At the back end, this is constrained by the schedule of the electron-ion collider under construction at Brookhaven. But we'll definitely try to make the absolute best of the 3 years of running that we have, concurrent to further running at the Large Hadron Collider. I mean, this is a collection of performance plots. I don't think I have time to go through all of them, but what they illustrate here, for example, is how much the capabilities of sPHENIX enabled by new state-of-the-art detectors improve the measurement possibilities at RHIC from what is there now, some heroic effort by STAR, to what the new Vertex detector at sPHENIX will enable. And similar improvements are possible for the kinematic range of particles that we detect, the momentum resolution with which we detect decaying resonances, and the precision with which we can measure jets using the first hadronic calorimeter at RHIC. Let me just show one detector that I particularly like because MIT provided the mechanical construction for this. This is the Mvtx micro vertex detector. It's 3 layers of extremely thin silicon detectors with hundreds of millions of pixels, which will allow us to observe the decay of particles containing heavy quarks with high precision. Essentially what we do is we take the heavy quarks that nature has provided with masses that are 5 to 20 times the temperature scale of the quark-gluon plasma, and we see how do these heavy quarks get kicked around in the quark-gluon plasma, which allows us to measure, in essence, the in-medium QCD drag force on these heavy quarks, characterized typically by the diffusion constant ds. So seeing how heavy quarks go with the flow is one of the key measurements that we will perform at RHIC, because that gives us another handle on the liquid nature of the quark-gluon plasma and can be turned into an independent measurement of the shear viscosity. Let me just point out, I was hoping that by now this detector, which was assembled at Lawrence Berkeley National Laboratory, was on its way to Brookhaven, but it's still stuck at Berkeley because someone ordered a 60-foot truck to transport it. Everybody who's ever been to Berkeley knows that, well, you can't get up the hill with a 60-foot truck, so now we had to order a truck that's half the length. Supposedly it's going to start its way at 6 p.m. today or before 6 p.m. and then a few days later should arrive at Brookhaven. This is sort of a $5 million device that a few dozen people have spent the last 4 years of their life putting together, and well, one good pothole on this in this 3,000 miles will put an end to that. So this is really exciting, and of course, it's not even insured. The Department of Energy is self-insured, but in the end, it wouldn't matter because it would be impossible to rebuild that in time for using it in sPHENIX. And again, what we will be able to do is measure how much do heavy quarks participate in the hydrodynamic flow with much higher precision than was possible at RHIC before, for both charm quarks, which have a mass of about 5 times the temperature, and B quarks, which have a mass of about 15 times the temperature. So that will allow us to measure this diffusion constant, the heavy quark diffusion constant, with more precision, much higher precision at RHIC than before, which will be combined with the data from the LHC to determine the temperature dependence of this transport coefficient, which will allow us to distinguish between, let's say, a point-like description of the quark-gluon plasma in terms of quarks and gluons, which is already ruled out by the present data, and then we'll be able to see how much does this system really approach the structureless liquid that the flow measurements that I showed before seem to indicate. So this will be, I think, one very exciting outcome of RHIC. We will also be able to do new jet measurements at RHIC with the first hadronic calorimeter at RHIC, but I'm not going to, I don't think I have time to go into the details there, so let me just skip over that. We'll do Rutherford scattering of the partons inside the quark-gluon plasma. But, and then let me come to the summary. So what we have learned over the last decade or so, 2 decades, is that in collisions of heavy ions, we can indeed produce a system at temperatures that are nowhere else to be found in the universe, trillions of Kelvin, not seen since a microsecond or so after the Big Bang. The state of matter called the quark-gluon plasma. And we see that this quark-gluon plasma, far from being boring, has, as anything else in QCD, very exciting emergent properties. It is an almost perfect liquid, as perfect as we have seen anywhere in nature. It is extremely opaque to high momentum quarks and gluons. They get, you can take a quark that has an energy of equivalent to the mass of a gold nucleus, send it through the quark-gluon plasma, and sometimes it will be stopped over a range of just a few femtometers. And well, while we have discovered these properties of the quark-gluon plasma, we are still trying to understand how do they emerge from the underlying interactions of quarks and gluons. And that's really the program for the next years at RHIC, the next years at LHC, and up to the next decade or more overall. And we hope that the sPHENIX collaboration will make a decisive contribution to really understanding how does quark-gluon plasma work. And that's, I think, as far as we get today.
Okay, thank you, Gunther, for a nice talk. So we have time for questions.
So I'm just looking at this slide, and you have a statement of a bullet which says no quasi-particles seen yet in scattering experiments, and I was wondering what kind of quasi-particles you were expecting to see.
So that's a very good and very difficult question. I would say the ideas of whether there's a quasi-particle description of the quark-gluon plasma at certain temperatures, and what quasi-particles we might be looking for is still in a very conceptual stage. And here's one example based on UGP monopoles that are postulated to exist in QCD and QCD magnetic monopoles that are postulated to exist, and that at least in this models. Let's say, championed by Shuryak and Gilashi and others, would show, a significant population of such monopoles in the temperature region, so shortly above the critical temperature of about 150 MeV. Now, I'm not sure whether I would put an enormous amount of stock into this particular prediction. But the idea in this and similar models is that the interesting stuff is supposed to or expected to happen in a temperature region of, let's say, Tc to maybe 2 times Tc. And then things gradually get more boring as you go to higher temperatures. And that's some of the key motivation behind running both RHIC and the LHC, where with the 2 different collision energies, you start the quark-gluon plasma at different initial temperatures. You get different trajectories in, let's say, a density versus temperature evolution. And then by combining data from the 2 regimes, you may be able to isolate effects in a particular temperature range. And as I said, this calculation using showing how the presence of the quark-gluon monopole plasma changes, for example, the extraction of eta over S. It's one of the examples of the quasi-particles that might be expected. I think there's a lot more work needed on the theoretical side here.
Other questions?
Do you get the equivalent of a shock front if you're running two of your nuclei together, like you would in a MHD or hydrodynamical situation?
And that's an interesting question, partially because that goes back to the prehistoric times of the field of heavy ion collisions, where shock waves were predicted and, let's say, discovered in low energy, well, they were predicted and discovered multiple times, which usually is not a good sign, in low energy heavy ion collisions. I think in the hydrodynamic, in the bulk hydrodynamic evolution of the system, of the long wavelengths evolution of the system described by low viscosity hydrodynamics, shock fronts do not play a significant role. Where they become interesting is when you take a high energy quark or gluon and then send that through the liquid. You can see structure, I mean, excitations induced in the density distributions that are related to the propagation of a very fast, strongly interacting particle through the liquid. These have been well, also predicted for a very long time, but are very difficult to observe because they're easy to calculate in momentum in configuration space, but very difficult to find in momentum space, which is what the experiments actually see.
Okay, Doug.
So this might be a trivial question, but early on you showed the animation of the collision, right? And you showed the cloud expanding and the quark-gluon plasma sort of, you showed things condensing out of the quark-gluon plasma. And I noticed that the quark-gluon plasma itself, your red matter, seemed to persist for a very long time at the poles. Yeah, you had it clearly on your in the still picture too. But
okay, this is
yep. Yeah. So I guess I'm wondering is there some simple kinematic reason why the red stuff survives?
Okay, so everything is moving at close to the speed of light, but just by kinematics, the stuff that is closest to the front, by definition, is the stuff that is moving the fastest, because that's how it got to the front. So the fluid cells there are moving at a much higher velocity in my observer system, and therefore the quark-gluon plasma in my time lives longer there. Yeah.
Okay, so I think it's good time to stop here, and let's thank Gunther again for the nice talk. So we can continue the chat and discussion outside at with cookies.
I'm not flattering. I really enjoyed it. Let me pause the recording.
So I didn't know about this brilliant